See, at the time, my friends and
Right.
I
Right.
rode the bus or something, went to the World's Fair.
Well, when I was very young, I used to hop on my bike and ride down to the park where they had built World's Fair. And cool.
I went to that World's Fair.
Yeah.
We drove
I
down
have
from
the
Connecticut.
book.
We stayed in a motel,
Yeah.
with our neighbors.
We have the original book that you bought when you got there, the guidebook. We still have it. Probably
General
not.
Electric. Remember the General Electric exhibit?
Absolutely. I
Yeah.
love that exhibit. Absolutely.
It took you through the generations with all the different things that GE did for the home. With these,
Yeah.
they had robotic people that
Right.
look, women and talking to you about their new refrigerator and stuff. It's really
That's right.
state of the art.
And some of the buildings are still standing. The one that had the restaurant up at the top, it's
Yeah.
still standing. They've painted it. There's a group of people that are trying to keep restoring what's left of it. And the big globe is there. And when you go to the stadium, the baseball stadium, you can see the big globe. You walk right by it, depending on where you park. Because
Cool.
we go to ball games at the new stadium, the Mets Stadium. So,
So let's see, today, Scott, I'll tell you what, these are nice short intros. I think just to keep it simple, I'll do the intros. I like to do that anyway. It makes it more of an event if you do intros, and white people can know who these people are. And
Yeah, I think that's a good idea, Bruce. And can you record mine separately?
no, I can't.
Oh, really?
I have to record them all at the same time, or I don't record them at all.
Maybe we could splice them afterwards or something, or?
Yeah, you could take it and do anything with it, but I have to record the whole thing. But
right.
once it's recorded, it can be cut down. I've never done that myself, but I know it can be done.
Am I
Maybe
going
someone
first,
could
Bruce?
give a little spiel about how to do some of these video splicing things and all that. That would be nice.
That would be a good talk,
Well,
actually.
you just go to Google and say, Google, tell me how to take a video, and it'll tell you exactly how to do it.
I have asked Google God, but wasn't very helpful.
Oh, really?
Anyhow.
If I figure it out, I'll let you know.
Thank you, Bruce.
They have software you can use that just download the app. Dave, you coming? Yep. Okay.
Yeah. Yeah, so we need to get April 14th filled in, but that's another matter.
Would you do me a favor though and change the title a little bit on the one I'm going to do on the 2nd?
Yeah.
It really should be microscopy in the world of the very, very small. That's my emphasis.
Oh, okay. I thought that's what microscopy was.
Not the way I'm going to do it. I mean, very small.
All right. In the world of the very small. Okay.
Yeah, I've given that talk before. It's fun to do. So
Good. I will do that.
okay.
In fact, I need to get titles from numerous people right now.
Oh yeah.
But
John?
at least we have a good lineup of speakers. It's going to be.
Yeah. We don't know what most of them do.
You've managed to fill this thing pretty well. You've never had a gap, right?
That's right. Well, we had one when we had when you were going to speak.
Well, yeah, through natural disaster. Get that.
We had 9 days without power, Scott. It was kind of like camping for 9
Well, it
days.
was cold too, right?
It was cold.
Yeah.
But we have now a fireplace insert. So
Okay.
we had them put it in yesterday. So no more chilliness. Well, I think we should probably get started. Today we're going to have 3 speakers, and each one of them is going to go 10 to 15 minutes. It's not a contest. At least I hope it's not a contest. And the first one is going to be Scott Diamond. And the second one's going to be, I've got to make sure I get your name correct. I call him Ripey because that's what it says here, but it's Ripudaman, right?
Ripu.
Ripudaman Malhotra. Is that right?
Yeah, or just Ripu.
Ripu?
Okay.
Ripu,
Okay.
R-I-P-U is good enough.
Got it. Okay. And then the third one is John Miller. And so here's Scott's abstract. It actually his bio, and it's very self-effacing. Trust me, he has a whole lot more than what it says here. But Scott loves physics and math, and like Scotty in Star Trek, has been known to read technical journals for pleasure. He has degrees in physics from UC Berkeley and Stanford, PhD, by the way, but left the Bay Area for Portland in 1989 and never looked back. When not exploring the amazing outdoor activities available in the Pacific Northwest, he is working on a special project at FLIR. Scott Diamond.
Okay. Thank you, Bruce. All right. So the title of my short talk is Life on Earth. And so let's start back at the beginning of Earth. Earth is about 4.6 billion years old. And the first eon was the Hadean eon, which lasted about 600 million years. And as I'm showing in this portrait, it was a pretty inhospitable time. I understand that during this eon, a planet the size of Mars smashed into Earth and ended up creating the moon that we have today. The next eon is the Archean eon, which lasted an impressive 1.5 billion years. And in this picture, you know, it looks pretty nice, but pictures can be quite misleading. And that eon certainly didn't start out as friendly as this picture shows here. So this is the early Archean eon and present day, and a few things jump out, of course. If you look at the early Archean, first is that the planet is mostly covered by water. There are just a few land masses, and the oceans are all green. And the reason the oceans are green is because there was a lot of iron floating around the oceans. And normally iron reacts with oxygen and makes rust, but there wasn't any oxygen in the atmosphere at this time. At this time, the atmosphere was mostly nitrogen and then carbon dioxide and a fair amount of methane. Now, about 3.5 to 4 billion years ago, something big happened. And as you can probably guess what that big thing is based on the title of my talk, and that is matter begets life. And so I'm not religious, I'm an atheist, but when I think about life forming spontaneously, it's hard not to use the word miraculous to describe that. You know, you think about the fact that you've got just matter, chemicals, you know, in chemical form, you've got matter, you've got some energy being input to the system, and you've got a whole lot of time, and out of that combination, life comes. And I really think that's astounding. So it does kind of bring up the question, though, what is life anyway? And there's really, from the little reading I did, there's not really a universal agreed upon definition of what life is, but I can say a little bit about it. You know, there are complex molecules. Here I've got a picture of a protein molecule, and then this is just some other molecule I pulled off the web. I don't know what it was, but they're complex molecules, but those are not considered to be life. Crystals. So the number of rules that people have put in place for what life should be as far as growing and multiplying, things like this. And it turns out crystals obey a lot of those rules, but you know, people don't consider crystals to be life. Maybe more interesting is viruses are not life. So here's a picture of coronavirus that we all know so well. And I think a lot of you might say, well, that seems like life. You know, it replicates, gets all over. We talk about it like we're fighting a living organism. But I would say viruses are in the gray area, but generally viruses are not considered to be life either. So like I said, there's not a definition everybody's agreed to, but one of them that I saw and that I'll use is that life is replicating and self-contained metabolism. So the early life that first happened on Earth was anaerobic bacteria, like I'm showing here. Anaerobic meaning without oxygen. Now, compared to the life that we see today, it's very simple life, but considering it just came out of matter, it's really, again, it's miraculous is the word that comes to mind. I mean, bacteria, it doesn't have DNA. The first one had RNA, which is a really complex molecule. It has metabolisms, it's able to replicate. You know, it's really astounding that this bacteria evolved. And there are differing theories about what the conditions were and what it was that caused life. And I'm showing pictures of some of them here. So there's thoughts that lightning hit the water and that provided energy to make particular chemicals that then caused life. There's a theory that there was a naturally occurring nuclear reactor under the ocean with water flowing through and a number of conditions that allowed life to develop. There's theory that there were the fumaroles and that provided chemicals and that these fumaroles provided the necessary ingredients for life to form. For whatever reason is the bacteria formed and then they spread out throughout the ocean floor. They were living at the bottom of the ocean at places near these fumarole-like things where there was nutrients for them to survive on. And things were fine for the planet for about 500 million years that these anaerobic bacteria were living. And then about 3 billion years ago, an upstart appeared. And this upstart is really kind of the star of the talk that I'm giving. And this is what got me inspired to talk about this topic at all. And I'll make some analogies, I think, between the life, the progression of this upstart and humankind. So the upstart, as I think many of you know, was cyanobacteria. So cyanobacteria, also called blue-green algae, but it's really not an algae at all in the sense that we think of algae as a plant. It really is a bacteria. Cyanobacteria did something really remarkable that no organism had done up until that point, and that it was able to combine energy from the sun as opposed to getting it from sea vents on the bottom of the floor, and use water for processing energy. And so the chemical reaction that happened is I'm showing here. You've got carbon dioxide and water, and then with photosynthesis, the miracle of photosynthesis, it was able to convert that into a carbohydrate, into a sugar, into energy storage that the organism could then use to live on and then multiply. And then as waste products, it output oxygen and water. And I'd say, you know, again, there are now analogies to humankind as far as kind of how prolific this thing was. So cyanobacteria then spread throughout the whole planet and thrived. And you can see that here. I'm showing a picture of the graph of the oxygen concentration in the atmosphere. Like this is 20%, and this is a timeline in billions of years. So this is 3 billion years ago, 2 billion years ago. And the green and red bars are kind of, or lines are the actual value of oxygen. They think is somewhere between those two values, right? And at first, the cyanobacteria appeared, I don't know, sometime around here. And at first, there wasn't a lot of oxygen in the atmosphere. And the reason is that there were other elements in the Earth's crust and the atmosphere that would react and combine with that oxygen and absorbed it. And it wasn't until all those sources became saturated that then the excess oxygen really made into the atmosphere. And we eventually end up with like 20% oxygen that we see today. And there's very clear geological evidence of this happening. There's something called banded iron. So I said earlier that there was a lot of iron in the oceans, and that iron then reacted with the oxygen, created iron oxide, settled down to the bottom of the ocean, and formed its sedimentary layers, like I'm showing here. And geologically, you see this occurring, you know, something like 3 billion years ago, and you don't see it occurring before that time, which is, I think, is fairly clear evidence that oxygen, you know, appeared at some point and did not exist prior to that. So these were very prolific organism. It did really well, but there was a problem they faced, and that problem was waste. So basically, this organism produced oxygen, and it's kind of oxygen wasn't doing anything for the organism. It was its waste, and to some extent, you could say it was living in its own defecation. That it was putting this oxygen out into the environment. It was terraforming Earth effectively with this oxygen, and there were some consequences of that. So one was that this anaerobic bacteria that had survived for 500 million years before the cyanobacteria came along was wiped out. So basically all life before the cyanobacteria was anaerobic, and all of that life was wiped out, and there was only cyanobacteria on Earth. Now there were a few survivors down deep in the bottom of the ocean in a few of these places where the oxygen didn't get to, but for the most part, life other than cyanobacteria was wiped out. And the other thing, and this is kind of an analogy again to humankind, you have an organism that's wildly successful that's polluting its atmosphere. Well, the cyanobacteria almost killed itself as well. And the reason that happened is, I said earlier on that initially the atmosphere had a lot of methane in it, and methane was an excellent greenhouse gas. It's about 30 times better of a greenhouse gas than carbon dioxide is. Well, that methane reacted with the oxygen, and you ended up getting CO2 and water, but you basically removed all that methane from the atmosphere. The result of that is snowball Earth. This is called the Great Oxygenation Event. It was the first major extinction in the history of our planet, and 99% of life on Earth died. This is called the Hurrian Ice Age, and it lasted an amazing 300 million years until the planet finally recovered. So, it's pretty interesting. Again, there's some analogies with humanity that this organism was so successful, terraformed its planet, polluted its planet, almost wiped itself out. Now, fortunately, as we know the rest of the story, Earth recovered. And the interesting thing is, of course, we all owe a debt to cyanobacteria. The oxygen it turns out that you can get much higher energy reactions with the oxygen. And so it allowed much more complex, sophisticated life to evolve, including, of course, humans, right? And so it's to this cyanobacteria that we owe our existence. And in the last couple slides here, I want to talk about maybe what our path humanity is going to follow, and whether it's going to be like cyanobacteria. So I'm showing here Earth, as I said, has been around about 4.54 billion years in existence. And cyanobacteria has had an impressive run. Cyanobacteria has been around for 3.5 billion years, and it's with us today. Actually, it's quite prevalent. And if I compare it to some other species, the most obvious one that comes to mind is dinosaurs. So dinosaurs were around 165 million years. And if it wasn't for that darn meteorite, they'd probably be around today. And then on this time scale, I'm showing humanity. So human in some form has been around for about 5 million years. So on this scale, we're really nothing, right? I mean, we're so insignificant, right? And in fact, I'm going to zoom up on this or show it another slide here. So here's the same thing. Now, I also want to say I had the 5 million years for humans, but humans as we know it, 5 million years maybe for the first thing that we could call human-like, but we only invented fire about 1.5 million years ago. Homo sapiens have only been around for 200,000 years. Language has only existed for 150,000 years. And we just crossed the land bridge into North America only 20,000 years ago, right? So I think we're often full of ourselves and think what an amazing future we have, right? But I wonder how long we'll survive, right? Will we survive 20 million years? 200 million years, 500 million years, a billion years. You know, there's a Copernicus model that you can use that saying how long something's going to last based on how long it's been a bit around so far, and assuming some randomness. And that model says that humanity at most will last about 7 million years. And, you know, I think there may be some truth in that. I think in the same way that cyanobacteria kind of terraformed the world and allowed more intelligent life to evolve, that may be our role as well, except in our case, I'm going to suggest that perhaps our role is to spawn artificial intelligence, and that will be the natural progression of humanity into artificial intelligence. And the last thought I want to leave you with then is, how do you feel about that? You know, science fiction has all these pictures. This picture from Terminator, machines taking over the world and killing humanity, and how horrific it is. And I'll suggest that, you know, maybe it's not so horrible, right? You know, I mean, it gets to the point of what's your, none of us are going to be alive to see this, right? So what is your allegiance to? Is your allegiance to, you know, your country, to your race, to your species? You know, I'd argue maybe not, that there's nothing wrong with, insofar as we owe our existence to cyanobacteria and how they transform the population, that artificial intelligence may be the natural thing, and we could be proud that that's the way that we've evolved as well. And we're not tied to biological carbon-based identity. Okay, that's it.
Thank you.
Yeah, here we go. I got to get myself.
Let me stop.
I like that attitude.
Let me turn off the stop sharing here. Yeah, a little bit sci-fi, but I thought it was fun.
All right. So let's get myself here. That was awesome. Absolutely awesome.
I
Thank
agree.
you.
Absolutely.
Yeah. So let's move on from the robotic future to whatever Ripu is going to say. So Ripudaman Malhotra has over 35 years experience working on a range of energy-related projects encompassing process development, mechanistic studies, and chemical analysis of resources and fuels. He has worked extensively on the processing and analysis of fossil fuels and advanced materials. His work on coal liquefaction and pyrolysis resulted in identification of novel pathways for hydrogen transfer by which strong bonds in coals are broken. He currently is investigating pyrolysis and gasification of coals at elevated pressures under conditions using radiant furnace that allows complete capture of all the products for detailed mass and element balance. Lately, Dr. Malhotra has been studying the applications of biotechnology in the areas of energy, chemicals, and the environment. He's a recipient of the 2015 Henry M. Storch Award from the Energy and Fuels Division of the American Chemical Society. Ripudaman Malhotra.
Where did you get that?
LinkedIn. I'm sure you wrote it.
I don't think I ever sent that to you. I would have sent something quite different.
You didn't send it. I found it.
Okay.
Sorry. Hope it's okay.
Scott, thank you very much for your talk. You know, that last slide was very sobering. And I think maybe Harold showed this or some version of this slide, and I like to look at this as an exercise in humility. I have a question for Harold or whoever may know more about it. They talk about the composition of the universe in terms of ordinary matter, then there is dark matter, and then there is dark energy, which is the largest part. I think, can you see my pointer or no? I don't know. Okay.
We see it.
Where's ordinary energy? Is that part of ordinary matter?
Yes.
So that the 5% includes the ordinary energy also, correct?
Yes.
Yes,
Okay.
but by relativity, they're equivalent, equals.
Yes, so their equivalence has been rolled in. I just wanted to be sure. So it should be both ordinary matter and ordinary energy. So anyhow, when we talk about energy, I just like to remind us how little we know of what else is there over there. And so some humility is in order.
Dark energy was only discovered in 98. So it's very recent. We even knew about that.
Say what?
Dark energy was only discovered in 1998. Even knowing that it exists is very new.
Okay, thank you.
And as of 4 a.m. Pacific, 3 a.m. Pacific time yesterday, there was released a discovery at CERN that says we know even less.
Oh, okay. Thank you for reminding us.
We're gonna have to save a lot of this till later because John Miller insists that he is able to get his talk in today. So
sure. Anyhow, I have been concerned myself for the last many years now about global energy, and it's what Scott was talking about. What the cyanobacteria, or some of them did. It produced oxygen, so and then led to its own demise. So not entirely, but really a whole lot of it. And we are concerned with a similar challenge. We are putting in too much CO2 that has some nasty consequences. And we face a tough energy challenge. How do we cut back the emissions of CO2 to save the planet? There's only one planet, Earth, that we know of. This is our existence. This is where we live. But I think we also have to reframe that debate about energy supply, because we can't be concerned. Sure, we have to concern about ourselves about the planet, but in talking about sustainability, you got to remember that that word sustainability shares a root with the word sustenance. And sustenance for our society comes from consumption of energy. It's absolutely essential for our food, for water, for medicine, for transportation, for all kinds of things that we do. And not providing adequate amount of energy has terrible, terrible consequences. There are too many premature deaths because of lack of energy. And about 3.5 billion people today on the planet still have substandard amount of energy available to them, which means no clean water, not enough food and stuff like that. So let's say we recognize that the current practices of energy production and consumption are unsustainable. But we recognize that energy use is central to our way of life, and consequences of not meeting that really are dire. And so there is this tension between protecting the environment and social justice. And that means a comprehensive energy policy must acknowledge the magnitude of the problem. That's how we begin. So what do I mean by when I say must acknowledge the magnitude of the problem? That generally means asking question, how much energy do we need? What are we getting it from? How much are we using? What will we need tomorrow? And stuff like that. Well, so let's start answering those questions. First question, well, we get energy from many sources. Today, mostly it comes from oil and coal, then followed by natural gas, some hydroelectric power, some nuclear power, some wind and solar and stuff like that. Well, so it's a good question to ask, how much energy do we use? But we immediately confront this Tower of Babel. We get energy from all these sources, and each of these sources comes with its own set of units. We always talk about oil in terms of gallons or barrels. We talk about tons of BTUs for coal. When speaking about natural gas, we talk about SCUFs or standard cubic feet, or sometimes BTUs. And all the electrical supply things, they're in some kilowatt hours or some multiples of these. And the lack of uniform units, and I've seen these things in many times in papers and articles and reports and whatnot. On the same chart, they have all these units rolled together. Each of these things talked about differently. We don't know what the conversion factors are and how they are talking about. This lack of uniform units presents a serious impediment to carrying on a meaningful discussion. And another thing is that each of these units by themselves represent a very small amount of energy, forcing us to use mind-numbing multipliers like millions, billions, quadrillions, and so on. It would be nice if we could have a common basis. That's the first thing. And so that was what the genesis of this cubic mile of oil that some of you have heard of, and Scott actually talked about briefly, and that's the title of the book that I co-wrote with Hugh Crane and Ed Kinderman. It was Hugh Crane, while he was waiting in a gas line in the 1970s, when he came up with this notion. Hugh was very facile with the big numbers and all that. He used to do all kinds of amazing calculations straight in his head. So that day he was just pondering the question, how much oil does the world use? And he made some quick estimates, look how many cars and how frequently put the gas in and stuff like that. And he came up with some number like, say, 600 billion gallons or something. So then he started wondering about, well, how large a pool would I need? So the line was long, so he just did some more calculations and came up with the notion that if we had a pool that was a mile wide, a mile deep, and a mile long, it would then be about 2/3 full. And he said, well, why don't we talk about all, instead of tons of coal and trillions of cubic feet of gas, put them all together in some unit, always in a framework like a cubic mile of oil. At least I can make a mental picture of this and relate it all together. So here's a little thing, that Statue of Liberty that I'm showing over there down there is in a red circle. That's like I'm zooming into it, because without this tenfold magnification, the thing would barely be discernible. We have all been to stadia, so I like to give another visual of personal experience. Go to a large stadium. Imagine 600 yards and 20 stories tall and stuff like that. And imagine that this is really a kind of a cylinder of this size. That's only 1,000th of a cubic mile. So 1,000 sports arena would be 1 cubic mile. So it's a fairly large number. Well, it's large, but it's also on a global scale, not that large. When I take a map of the globe and expand it fully to occupy the full screen on my device, 1 pixel is about 4 miles. So this is 1/4 of a pixel on a side. So it's big and small. We need to remember that together. In terms of energy equivalence, this is about 1.1 trillion gallons of oil, or about 26 billion barrels of oil. A CMO, a cubic mile of oil, that's about the current world consumption. It's 153 quadrillion BTUs, or quads. It's like 6.5 billion tons of hard coal. And now here come to an interesting one, electricity. How do we relate electricity to it? In physics, it's very easy. Take the BTUs that you have, and 3,412 BTUs is a kilowatt hour. But if we look at, in terms of energy for the way we use it, if one source gives me kilowatt hours directly, like a solar panel, it's given me a kilowatt hour of energy that is eminently fully usable. This is the exergy of it is also 1 kilowatt hour. Whereas a kilo of the 3,000 BTUs, to get to that 1 kilowatt hour, I'll have to burn something like 10,000 BTUs of natural gas. So we have to put in some equivalent factor, which is the conversion factor in there, what it takes. So if a solar panel or a wind source is giving me a kilowatt hour, it is displacing not just 3,000 BTUs, but something like 10,000 BTUs. That's an important thing to remember when comparing these things. There are unfortunately many compilations that do not. And most notably, the International Energy Agency still uses 3,412 BTUs, which is the physics equivalent. And I don't quibble with that, but you got to remember with that then you do get answers that are not exactly relatable. Fortunately, the Department of Energies and also the BP, as a statistical review of world energy, they have used some kind of a conversion. It may not be exactly 10,000 BTUs, which is what I happen to use in the book that we were writing. It is close enough. And when we finally, this is the energy, not the power. And power and energy is another of my favorite rants. People confuse, and the newspaper reports always confuse between the two. Energy is the stuff that we will also use, and the rate at which it is being used is the power. In terms of electrical for supply to homes, energy, total energy is important, as well as the power rating is important. A CMO per year is equivalent to about 1.75 terawatts. So I know when we get a gigawatt, you need 1,000 of those to get to a terawatt, and 1.75 of terawatts will be then the 1 CMO. But let me talk about personal relations also to what's a BTU. I'm showing you the picture of a BTU. I would also like to show you what a kilowatt hour looks like. I'm not much of an athlete. I think Scott could probably do a whole lot better, but when I go on an exercise cycle and I look at my meter over there, used to say about 125 watts. At that rate, I was really sweating. So it means that at that 170, if I did the cardio for 8 hours at a stretch at 125, which is I'm really sweating, huffing and puffing, I would produce 1 kilowatt hour of electricity, 8 hours of cardio. It's something that we could get for what, about 35 cents? So that's not bad for a day's work. Here are the trends for the global primary energy consumption. I'm sorry, it just jumps. I'm going to take this out of those pictures are interfering. This is in CMO units, and I have taken this from the BP Statistical Review of World Energy. You can see changes are happening, but they're very slow. The only thing that has changed significantly is this orange line, which used to be barely there. These are the renewables. This is where the renewables are, wind and solar. And the thing is, how soon can we expand it to meet our full needs, and how much our full needs will be. I think I'm going to save that for another time, maybe April 14th. That's not a bad date. If that's an open date for you, Bruce, you can let me know. And this was my rant about the fact that we don't have common units of energy, and they really cause problems. And mixing between power and energy is another source of problem. There are other things as well, but in the interest of keeping it brief and leaving time for questions, I'm going to stop right here.
Thank you, Ripu. That was Ripu. That was great. And those are, I'm a mechanical engineer, and when I went to college, we had to negotiate all those different things when we took our thermal classes, and I got very good at that. In fact, even today, I make a lot of those transfers.
Yes.
Some people that are trained in Europe don't get to do that. And they're probably happy about that in some cases. Well, our next speaker is John Lester Miller. And I think you're going to need to unshare your screen, I think, before John can.
Yeah, I can't share. Okay.
Okay. John Lester Miller has written 5 books, 4 with Dr. Ed Friedman, who's giving next week's talk. Actually, not next week's talk, but last week's talk, and over 100 papers on electro-optical systems. He is current chair of our planet's largest conference in infrared technology, chaired it several times in the past, and as well as the classified military sensing symposia. He has a BS in science and physics from USC and graduate degrees from Cal State Long Beach, University of Hawaii, and Regis College. He has over 40 years experience in infrared technology and phenomenology. This led him to do much research and consulting into biomarkers for exobiology, which he gave a talk on. And he is currently a consultant and runs his own consulting company. John Miller.
Thank you, Bruce. Yeah, I want to say 2 things. First of all, Ripu, I totally agree with you about semantics. That's important. And all the crazy units. You know, I don't understand why we can't all use calories like Scott did on a talk a while ago, or herbs. But anyway, and Scott, yeah, one of the biomarkers is just oxygen on the planet. Because like you said, it's so reactive. After 1 million years or 2, planet won't have oxygen unless it's being produced by photosynthesis. And I'll get into that a little bit. So I have 3 kind of random rants about energy, one about the universe. My vehicles, I like to say when I go on a first date, I have solar powered cars. That always impresses them. I have a Benz and a 4-wheel drive Toyota, and they're both solar powered. They run on gasoline. Gasoline is a fossil fuel using plant energy for photosynthesis, ergo solar powered.
Right.
Okay, really, they're nuclear powered. They run off the strong nuclear force and from the core of the sun. So they're really nuclear powered. Interestingly, and this is a little controversial and a little weird, but we could do a whole talk on this, but it takes approximately 100,000 years to 500,000 years for the bulk of the energy, I didn't say photon, I said the bulk of the energy created in a fusion in the solar core to be emitted by a photon or photons from the surface of the sun, which is really kind of interesting. It takes 8 minutes to reach, at the slow speed of light, it takes 8 minutes to reach the Earth, but the energy was actually created in a strong nuclear force long time ago. And one thing on one of my rants with Scott is renewable. Fossil fuels are the only renewable fuels we have on the planet. They're bad for the environment, but renewable. They are being renewed as we have this meeting. Albeit it will take several 100 million years to replenish what we already exploited. Solar and wind are not renewable. Nothing is regenerated or renewed once that photon's absorbed by the silicon. They are clean and green, but nothing is really renewable. As George Carlin said, it's a bad concept and it's bad for you. Actually, they also use fused hydrogen. So their solar and wind is also nuclear power from the strong nuclear force. Okay, another problem I have is people saying, especially companies, corporate America really likes to push this. We'll plant trees and you're carbon neutral. Bull baloney. Trees die. All trees die. They rot or get bug eats them and emit CO2 and methane. They burn and release carbon. Okay, small percentage may go into fossil fuels that's being renewed, but that takes millions of years. Shame on companies saying they can plant trees and make people think their airplane journey or their Subaru purchase is carbon neutral. Baloney. What planting trees does is a good thing, but what it does is it flattens the curve, as we all learned about flattening the curve a year ago. Because all trees die, all that carbon eventually goes somewhere. Now, it's good. I'm not saying it's bad, because flattening the curve allows humanity time to transition to cleaner energy sources. Also, global warming, which I like because I don't like the soft shell term climate change, is nonlinear. If we flatten the curve enough, and it's a big if, maybe we can stop the Siberian permafrost from melting. And that will prevent methane, which is an incredible greenhouse gas, from outgassing from underneath the Siberian. So it's not bad planting trees, it's good planting trees. But it doesn't sequester carbon forever. The lumber industry, the current lumber industry is very good for to reduce global warming. It transfers trees, not trusses, to wood, and wood has a lot longer time to decay. Lumber can sequester carbon for hundreds of years. I have a beam in my other house that's from the 1880s. That probably grabbed carbon from the early 1800s, and it's still in existence. Yeah, some people might buy a piece of plywood and throw it over a puddle in their backyard. In 5 years, it's gone. But generally, wood sequesters longer than trees, but it still all goes away. That beam in my house isn't going to be there 10,000 years from now. That carbon's going to be back in the atmosphere. Also, the lumber industry tends to plant trees to suck in carbon that they can also reharvest in 30 or 40 years or 20 years. It'd be great to plant bristlecone pines because they can last 2,000, 3,000 years. But the two problems with them is they're very slow growing. A 3,000-year bristlecone pine might only be 18 inches in diameter. And they're really finicky about where they want to live. So other species of the planet. And I want to talk a little bit, which I've never heard anybody talk about yet, and I don't know much about this, but the ultimate energy source for humanity. Whoops, what's it doing? Now it's jumping around again. Helium-3. This is why China is on the far side of the moon. The Chinese get it. In fact, it's been speculated that their rover has some classified instruments and classified data being taken for the Chinese government on helium-3. Because the far side of the moon should have a little more helium-3 than the near side. This could be a perfect energy source. Before I say anything, it's unproven. It's certainly embryonic. It's really almost not a technology. It's more of a theory at this point. And it is quite controversial. But what it is two helium-3 atoms fused to form a regular helium-4. Lots of energy is produced. No radioactive fuel is involved. It's not radioactive. No waste or no byproducts. In fact, what's produced is helium and protons. And the helium eventually leaves the Earth. And I'll talk about that in a minute. The Earth cannot contain helium. And there's also a version of helium-3 and deuterium. And you can boil water to make energy and run turbines. There's also the problem is you don't even have to do that. It just produces charged particles. And you would instantly get a higher efficiency electricity. The sun is the major source. It comes from solar wind. And what happens is, when you buy a helium balloon and that helium goes out of the balloon, it leaves the Earth's atmosphere. The Earth doesn't have the gravity to contain the helium. So we're bathed in helium-3 from the sun, but we got this atmosphere. It goes into our upper atmosphere, then it drifts away. Now the moon is 1/6 of the gravity of the Earth, but it retains helium-3 because it has no atmosphere. And what happens is the helium-3 embeds itself into the dust and into the regolith and the upper, say, 5 millimeters, 10 millimeters of the surface. This is a real surprise when we got the moon rocks back from the Apollo program. They were loaded with helium-3, and it took us a while to figure that out. Also, Jupiter has a lot of helium-3 in its upper atmosphere. Again, from the solar wind. Jupiter being much, much larger than the Earth is, the gravity, it can retain it in an atmosphere. It turns out this could be so efficient. Again, it's never been proven. The entire planet's energy supply could be made by a few shuttle loads of helium-3. This is controversial. Some dispute this and say it's actually much more. But the idea is robots would mine the upper centimeter or so of moon dust, take out the helium-3, put it in an unmanned spacecraft that delivers it to Earth. or we go to Jupiter and filter out from the upper atmosphere. The problem with Jupiter is it's so far away, and it's got such a big gravity, it's going to be hard to escape from Jupiter. The waste is not radioactive, and it leaves the Earth for space. The economics seem to work. If it took 7 shuttle loads a year, each shuttle could be worth roughly $1 trillion, because the energy industry, I believe the fossil fuel industry, is worth about $7 trillion a year. So this tends to work out, and China's all over it, and so is India. India, in fact, openly stated their lunar orbiter is looking for places to mine helium-3. I won't read through this. This is just some links to it on YouTube and some wiki data. Okay, my other little rant. The universe is not old, and the speed of light is not fast. I got really ticked off a couple weeks ago. I was watching a YouTube by an astrophysics professor. I forget his name, but he's from a major respected university. He kept saying, the universe is so old. It's so old. We're 13.8 billion years old. It's so old. It's not old. It's young. It's in its infancy. In fact, we are approximately right now living in the Big Bang. The universe is expected to exist somewhere between a Google and a Googleplex years. And we're only 13.8 billion years into it. It's an infant. The other thing that I have is the speed of light is slow, painfully slow, not fast at all. It takes about 1.3 seconds just to go to the moon, our nearest neighbor. When the Apollo astronauts were there, they were trained not to respond for like two seconds. But human nature is they often did and often over-talked to Capcom. The Capcom and them were talking at the same time. The recent Perseverance lander, they had to do it on autoland. It couldn't be controlled. Mars is too far away for the slow speed of light. The nearest star is 4.2 light years away. Imagine how nice it would be if the speed of light was like, say, 1 light year a second. It only took 4 seconds to get a signal to the nearest star. In conclusion, and by the way, if you want, I have time, I can explain Galileo's, that's his middle finger. He is flipping off the world to this day. And that's from the Galileo Museum in Florence. Well, we need to think total system-wise and more global system impacts of technologies and understand the system from birth to death and the total system. Electric cars from burning coal like they were 5 or 10 years ago is not good for the planet. Well, if we generated electric cars have geothermal power like in Iceland, that's pretty darn good. And semantics matters. We think in language, we legislate and regulate in language, changing language, laws, and perception. As George Carlin would say, semantics matters, and when you get it wrong, it's bullshit and it's bad for you. And that's my finger next to Galileo's middle finger.
I think that qualifies as a rant. Yes.
Yeah. Do you want me to tell you how Galileo's finger ended up in a museum? It's kind of a funny story.
Yeah.
All right. So Galileo was a scientist in Florence, and he lived in Florence, and he became a heretic and was put in house arrest, almost burned at the stake. So when he died, the Catholic Church would not allow him to be buried inside of Florence. He had to be buried in a cemetery outside of the walls where they buried other heretics, Muslims, Jews, and non-Catholics. And he became obviously very respected, very brilliant, and he was, the scientist of Florence. So around 100, maybe, I don't remember exactly, 100, 150 years after his death, the bishop decided we're going to put him in the main Catholic cathedral there. And that's where he's buried now, in a big, huge, nice marble mausoleum tomb. So the bishop contracts with a contractor, go out to the non-Catholic cemetery and dig Galileo up. So the contractor goes out, digs Galileo up, brings him to the church, and typical contractor, he goes to the bishop and says, that job was harder than I thought. You owe me more money. I want to increase the amount to pay. And the bishop said, no way, I'm not giving you an extra lira at all for this. You contracted to do that. So the contractor goes into the church, opens Galileo's casket, gets some hedge clippers out, clips off his middle finger, I think his forefinger and his thumb. And he goes down to like a glass blower in Florence and has them mounted in like these Fabergé eggs. And the museum acquired them about 100 years ago. So that's why Galileo's middle finger is still on display for the world.
Whoa. That is great.
This is Dan. I think it might be interesting if you look into the European middle finger, it is the middle finger, forefinger, and thumb, because that was the fingers they would show to the French that they still had. I'm trying to get this right. The bow finger. The bow fingers were very important to the English because they had the long bow. And the French would sometimes cut off their fingers so they couldn't use the bow. And so the middle finger and the forefinger, so it was like the V upside down, backwards, that, we had the V. And I would look into that, but I think that was the meaning of cutting those off, was that it was kind of giving them, it was the English giving everybody else the finger, so to speak. So it's not the same meaning as we have, but it's basically the same meaning.
Wow. Well, let's I think what we decided we would do is let Ripudaman and John and Scott, just if you have anything to say about each other's talks, say so, and then we'll open it up.
I think we really, it's not like I'm expert on these. I think we should just open it up to everyone anyway, right?
That's fine with me.
Yeah, I agree.
Okay. Well, Harold, you always have something to say. What do you think?
That was one. They were all wonderful. First of all, this was perhaps the most exciting night we've had. So thanks and thanks. Thanks. I'm just really. I wanted to make one question for Scott about whether to include this in life, and I too am mystified a little bit about what life is and even about how it sort of kicked off. But do we include anti-entropic? In other words, that we're able to maintain a state that is not in equilibrium with the outside of us? And the other comment to make is I'm fascinated about this Landauer stuff, because for those who know me won't be surprised, but I was a bad boy at a talk by one of Landauer's colleagues where I questioned the KT Laud 2, this idea that there was an energy cost to erasure in computing that could not be defeated. Got into an argument after the seminar. I'm polite, but whatever.
Well, I don't think you know how much I know about energy. I know even less about the last talk, so I can't really. I understand your comment somewhat, but I'll leave it to others to comment on that.
The comment on life is interesting. Whether you include an entropy criterion in life.
Yeah. Insofar you're saying as life is kind of like entropy increases, and at least locally, life conflicts and goes the other direction, right? I mean, is that your point, that you're seeing entropy decreasing locally, and that almost is a definition of life?
Yeah, I certainly read that. I mean, I don't have a good definition of it, and I like what you did. Viruses that can't self-replicate without us, or without some other way to carry it out. Yeah.
It's
Scott,
very
do you have anything?
controversial, actually, whether or not viruses are considered a living or not. It depends on who you talk to.
Yeah.
Because I've done a lot of research on the coronavirus, because I've written some articles about it, and every source, this one says, well, it's a living thing, and this one says, no way. The bottom line is it doesn't reproduce itself. it shoots the RNA into the cells. That's different. But you don't see it going from meiosis and mitosis to divide. And it doesn't eat. It doesn't take in nutrition. It just gets there, gets rid of its RNA, and it is done. And so, Dave and I have given some talks on what is life. And I've always said, viruses are not life as much as they seem to be when you look at them.
Yeah, when we talk about this, we list like 7 different aspects of life. And when we talk about the crystals, we say, well, they have 3 or 4 of them. So to really be life, you really have to have all of those things, and reproduction and interaction with your environment, and so on. So it is one of those really important, poorly defined concepts.
Right, and what I thought was intriguing, well, I picked up some of that in my reading, but there's also discussion, like I was talking about AI, is a computer virus life, and at what time does AI become life? And does it fit into these? I think at some point it could be considered life. And yet,
where is sentience in this?
Pardon?
This hierarchy of things, of the criteria of life, awareness, where does that come in?
That's right.
Yeah.
Well, we'll have Peter did a couple of talks on this for us. And maybe I'd love to get him back again, but I think he's getting busy.
One thing I noticed from this, if I may, this gives us an opportunity to select longer talks. Some of us would clearly be fascinated to hear more about life, and to hear about helium-3 would be fascinating. It's a nice teaser to give you a chance to pick bigger talks later.
Yeah.
Yeah, I think helium-3 would be a great talk. I'm not an authoritative enough to do it, though.
Oh, sure you are. If I can talk on energy, you can talk on helium-3.
Scott, I just want to say that next time I read a book or watch a movie where the human beings are fighting for their life against the robots, I'm still going to root for the human beings.
Okay. That's a short-sighted outlook, but okay.
Yeah.
But I'm happy with it.
Do you have children, Scott?
Pardon?
Do you have children?
Yeah, I do. Okay, so yeah.
So if you're a Darwinian, the purpose of life is your children.
Yeah.
You got to replicate your DNA.
Right, but should Cro-Magnon man be upset then that they didn't survive? I don't know. I mean, that gets to that whole thing of, like I said, what's your allegiance to? To your family, yes. To your species, to your country, I don't know.
This is Ed. I make a contribution on the topic of what is life. Erwin Schrödinger wrote a book of that title, which I read decades ago. So I don't remember anything about it, but he was diving into these issues, and it was written before the structure of DNA. I think he wrote it in maybe 1941 or so, and he speculated about what the replication technology we would discover would be, and he got it just about right.
This is Dan. I'd like to argue that if we can't define what is life, then how do we define what is gender? I get a kick out of this whole thing. You think life is a dichotomous decision that it either is or isn't. But we find all of these different mutations going down the road, and you say, well, is a virus life? Is a prion life? Remember these proteins that self-replicate, but they require a host, and they don't even have structure like, there's no outer membrane, there's no core. It's simply a protein that causes itself to replicate. So I kind of laugh when people say, well, these things are all very well decided. And then I say, well, what about gender? And it's like just such a mess. Everything's a continuum, but you talk about, like I said, viruses and self-replicating, and you got prions that self-replicate. There's nothing simpler than a protein, a misfolded protein. So
Reminded of Kurt Vonnegut. There's a Kurt Vonnegut book where a waitress and a truck driver discussing the secret of life, and they said, "Yeah, oh yeah, I think Professor Jones over at the university discovered the secret of life." And the waitress said, "Well, what was it?" And the truck driver said, "I think it was protein."
So he had it before the whole prion thing came along. It's perfect. Yeah.
Hey, Dan, seeing you here reminded me, I think, weren't you the one who spoke about the Novavax a couple of days ago? It was in news yesterday.
Yeah.
Briefly, I talked about vaccines, but no, what was that? The Novavax? What happened?
Well, they were, again, talking about that it's probably going to be a vaccine for coronavirus, for the COVID-19.
Yeah.
And they were being very optimistic, like a puff piece in the news item. And the CEO was being extremely cautious.
Okay.
But he was
This
there.
was this the broad spectrum, the broadly neutralizing?
Do not know.
Oh, no,
They didn't, it was on the news, 30 seconds or so. It's hard to tell what exactly they were talking about.
well,
Yeah.
Novavax,
The name.
I know something about Novavax. My neighbor, my next door neighbor that I grew up with is the chairman of the board of Novavax. And Novavax is the vaccine of choice for New Zealand. They have a contract with Novavax, and they've done almost all their study and are ready to release it. And it's the one that our vaccine expert, Ed Friedman's brother-in-law, says he wants to get, because it's the most traditional and isn't experimental. And
And it doesn't require the level of refrigeration that the others do. And they also say it's cheaper. They can make it cheaper. So the expectation is this is going to be something that's, when it's made available to the poorer countries, it will have a major impact.
Yep.
Yeah.
and one shot.
And one shot.
I thought all those attributes were, in fact, the ones talking about AstraZeneca. But in fact, you don't have to freeze it.
Yeah.
It's very,
They're
very cheap to
trouble.
make.
Yeah,
It's going through its tough time of bad PR, but
yeah.
it meets the criteria for the third world, particularly.
Yeah.
It may still be the most effective one.
Yeah, well, we had Moderna, but you have to think about that. It's hard to say there's anything good that came out of this virus we've lived with the past year, but they've started to at least use like messenger RNA in the viruses. That was the first time it's been used in humans. And I think it's going to take off now that we've used it for this, and also become a wonderful tool that will develop. Like I said, I hate to even use the word, the good thing that came out of this virus, but that's really impressed me when two of the drugs are based on messenger RNA. So two of the three.
Well, this is Ed. I want to echo what Judy just said and add something to it. I think the biggest factor, the biggest contribution that we've seen toward educating the public about science has been the miracle of producing a vaccine in 1 year. And no matter who you are or what your political affiliation is, everybody knows that we were able to do that. And the foundation of that miracle is that we're working at it all the time. The AIDS epidemic caused us to really get serious about understanding cell biology in a whole new way. And now we have a reward the 1-year development of vaccine, which actually was known a year ago. It took a while to figure out whether it was safe and how to produce it. And that, along with CRISPR's, the gene editing technology, is going to change everything for everybody. And so we have, I think, in spite of reluctance on the part of some people, we have a renewed interest in immediate application of our scientific investment. And if Joe Biden is smart, he will exploit this to expand the number of topics the NIH and the National Science Foundation pursue, because we don't know what the next risk topic is going to be. And we have to have the broadest possible foundation to use if we're exposed, and it doesn't have to be biological. It could be something else. In fact, and while I have the microphone, John Miller brought up something interesting about sequestering of methane, and methane being a very effective greenhouse gas. There's just recently a review done on the topic of fluorocarbons that are sequestered in the ocean, and that by 2075, ocean temperature rise will cause those gases that have been absorbed by the ocean to come out of the ocean and contribute to what will be an uncontrollable greenhouse event, because it's not gas we're producing now. It's gas we produced decades and decades ago that ended up in the ocean. And if the ocean is warm enough, we're going to get all the oceanic fluorocarbons will reappear in the atmosphere.
Yep.
Yeah, I agree with that and Judy. I'd like to add one more good point that came out of this pandemic. At least for the next 20 or 30 years, until we forget, we're going to take outbreaks seriously. We screwed ourselves with SARS. This is SARS 2. SARS 1 was what, 13, 14 years ago. We made some special cameras that FLIR for it. And it kind of went away and everybody forgot about it. I remember at the time a lot of epidemiologists with their head on fire saying, no, we can't forget about this. This could mutate. And basically, you know, we're paying for it now. So hopefully another good thing is we have our eyes on any kind of outbreak to contain it immediately as soon as possible.
You think it's possible to contain it, John? I just don't know if it is, you know, I mean.
Well, we contained Ebola. We contained Ebola.
Yeah, in a small.
Yeah, Ebola killed quickly. John, you're an optimist. My son works in viruses, coronaviruses and SARS, and we just don't want to spend the money. He says if we just
I know.
a few years ago, we'd have our arms around corona as it hit. I mean,
in fact, I remember Science Friday 3 or 4 years ago, Ira Flato had some woman on that she wanted to try to cure the common cold, which is coronavirus. And she pointed out this thing could mutate and get real bad. And she also pointed out the amount of GDP lost per year from the common cold was, you know, X billions of dollars. And, you know, for a fraction of that, they could get a vaccine. And even Ira Flato kind of poo-pooed her and said, yeah, but you get the sniffles and you get a cold. You're right. Hopefully we'll spend more in the future to get a head run on this. And you're right, Ebola is easy to contain because it kills so fast. But still, SARS went away, you know, and was contained. And we dropped the ball on SARS and MARS.
No, you're right. But you know, there's people who've been claiming this is going to happen, and nobody listened to them. Maybe now they'll listen to them. Maybe we'll monitor corona like we do the flu, and come up with the next 3 possible coronas over, you know, year over year. We'll come up with new mRNAs every year, or maybe new adenovirus, mutated adenovirus, but we'll see. I think the idea that this thing mutates so fast is scaring people enough in real time that they'll pay more attention to it. So maybe you're right, but I think you're an optimist.
John, there's a question for you in the chat, and I have a question for you too.
Okay.
Take the question from the chat that came first.
Okay, well, hang on.
I'll read it to you, John. A question for you, John, says, instead of planting trees, do you have a more permanent approach
to propose for carbon offsetting, for instance, buying and permanently reforesting acres of land?
Yeah, but reforesting won't help. I mean, that just flattens the curve. I don't have a solution. There are people working on carbon sequestration where you turn into limestone or you pump it into the ground or even into the ocean. The ocean sequesters carbon for a lot longer. Again, I'm not an expert on this. I don't have the answers. There are people working for it. And
I can talk about that. I can talk about that at length
trees
another time.
So John, there is a way to sequester in the ocean.
Basalt is the one thing. Basalt rocks are the ones that can mineralize it, and you will get quartz and limestone. And that's the two solids from a gas, and that's the only basic oxide that we have. Otherwise, it's all acidic, it's all oxidized, and CO2 doesn't react with it. But it takes energy. And so that's the permanent sequestration. Question for you, John, was about, you made in your rant, I agreed with most of what you were saying. Well, I heard something about the changing of the name, about not calling it climate change, as if the switch from calling it global warming to climate change was somewhat an appeasement of some kind of a political correctness. That's not how I remember the debate going. It was the fact that it became too complex. We realized it's not just warming, because it's warming and it's cooling and there are hurricanes and there are too many other effects that it's affecting the whole climate. And that climate change was therefore a better word.
Yeah, it is, but it's all driven by the global warming. But you're right, there are many other effects.
And so calling it global warming was missing the point, and people could take easy pot shots at it and say, hey, it's not warming here. Globally, it is being driven by the greenhouse gas effect, yes. But calling it climate change draws attention to the fact that there are many dimensions to it.
Yes, I agree.
There's
You know, John, probably the best long-term solution to climate change or global warming is a nice big juicy pandemic that knocks out about 3/4 of the human race.
The one thing no one wants to talk about is overpopulation. If we had 2 billion people on this planet, we wouldn't have global warming. I'm the greenest person on the planet because I did not reproduce.
Hey, I'm up there too.
But in fact, I think we'll get there, because if you look at much of the developed world, we're well below replacement right now. And this picture of AI helping, I mean, if the solution to an aging population, I think, is clearly not for governments to encourage more reproduction, but to figure out how to intelligently use AI, as has been here. And yeah, if we were 2 billion, Ehrlich was right.
What is the best way to control population? The best way to control population is to raise the standards of living.
Or have Scott's robots.
What raises the standard of living? Energy.
Yes.
Energy is what is needed. It took energy. A European population grew so many times before it levelized. Same thing in other places. America is the exception where population keeps increasing with high standard of living. But everywhere else, it's been otherwise. It's the importation, people like me coming in.
Yeah.
Also contribute to it, yes.
Actually, education of women is the best.
That's also exactly, educate women, and that's what controls population. And that's what, again, I emphasize, it's the need for much more energy, how much is needed, and how do we get that? I mean, yes, we can allow half the population of the world to die. Is that socially just? And then if you want to really kill the people then who are the ones who are currently consuming most energy or producing most of the CO2, not the ones who are barely eking by.
Okay, guess what? There's a you know, you've been talking about the square mile of oil and whatnot.
Cubic mile.
Cubic mile, yeah. Well, it just turns out that we have a repository for all of the human beings up at Mount St. Helens. It turns out that the entire biomass of human beings could fit into the hollowed out space in the
St. Helens.
volcano there,
Yeah.
3 times over.
It's amazing. Right?
So doesn't seem like there's really that many human beings to deal
No.
with.
Well, will they all be wearing masks?
Yeah.
I don't want to be on the bottom of the pile.
Okay. We'll put you on top, Judy.
So Scott, you're the pessimist about the future of humanity, yet we've been hearing about all of these wonderful increases in knowledge and in controlling diseases. You don't seem to be giving any credence to the idea that we might actually evolve enough to think our way out of some of the problems.
Not really. You know, it's funny. I'm kind of influenced somewhat by, I think, Edward, have you given the talks on the mathematics and stuff where, you know, it's beyond my brain. And as I listened to those, I kind of thought, you know, there's an AI that's going to come along that's going to be able to think in 20 dimensions like nothing. And I just think there's a limit to what we can evolve with this carbon-based life form. I'm not saying we're going to go away, but kind of the next level, next AI may be like us to cyanobacteria, right?
You're probably right. I mean, if you were a cyanobacteria and you could actually think, and you saw what human beings became, it would be, you know, like this morning I was grabbed onto an egg, and I cracked off the outside of the egg, and inside of it is this little tiny membrane between the shell and the inside. And how the hell did that evolve to that point? I mean, come on, it's crazy, and all that stuff creates a bird, right, that gets up and flies away. I mean, like you said, Scott, life really is an incredible miracle, no matter how you look at it, whether you're religious or not.
Looked up definition of miracle apparently involves some supreme being, so I don't use that word, but yeah, it's hard not to.
Yeah.
Right.
Well, I think we probably should close.
Well, I got a quick question for Dr. Diamond. Hi, I haven't seen you in a while since you've been around, Doctor. I appreciate everybody's conversation. It's great to listen to this, and I haven't been able to do a lot of them, but they're great. Dr. Diamond, and this might be something for running time, but have you thought about how ethnocentric your concern is? And that we may have been through this multiple times. I mean, we're only halfway through, to use one of the other discussion points was how old the universe is. And we're only, what, you said 4, I've heard 5.5. There's billions of years older star systems out there. And you know, have we, you know, are we going to interact with them? Have other people been down this track? And the Fermi paradox, which I thought you were going to get to, kind of deals with that. Like, where are they? And so the problems may not just be here on the Earth. It may be much bigger than that.
I don't have any insight. I understand your point. I think it'd be great if someone gave a talk on the Fermi paradox, right? That would be fun.
A friend of mine from the old days, he's actually doing a movie about the Fermi paradox in La Jolla, California is where he's based. I don't know where the movie is being based.
What paradox is that? The Fermi?
The Fermi paradox? Scott?
Fermi, like Enrico?
Great videos. But
Enrico Fermi. So
Yeah, okay.
the story goes, is everybody familiar with it or not?
I'm not. I like to hear.
Me neither.
I'm not.
So Fermi, Enrico Fermi, back in the early 1920s, 30s or so, when he wasn't working on his electromechanical, earning a Nobel Prize.
Yeah.
You guys probably all know the details of. He was sitting around with his colleagues and saying, well, you know, given the number of star systems that are out there, as many star systems as there are grains of sand on the planet, on the beaches, that would mean a lot of habitable planets. where are they? Where are the, we're not the only life form is what he was saying. And there's other ones, and why aren't they here? I think they came up with 10 different thoughts, of which some were alluded to in this group here. Some being that you just burn up all the energy, or you wipe yourself out, or maybe technologically you never figure out how to go travel faster than speed of light. Or maybe it's not possible. But anyway, they came up with 10 different scenarios to say, well, where are they?
Well, they may have already been here sometime in the past. Time is very long.
Yes.
So they could have been here. They might be
They
here.
have decided not to come back,
Or
depending on.
they're already here.
In another dimension.
You know, from
Yeah,
Star Trek.
Evidence.
You guys,
Extraordinary claims require extraordinary evidence. There's absolutely no evidence for any visitation.
But
fair enough.
Well, that can be argued too, that there is evidence, because there are all these ancient wall paintings that don't show things that are common on Earth. So where'd they get those ideas?
Some of the hieroglyphics.
They were humans. They were creative humans.
Yeah.
Don't distract from humanity. We were smart 50,000 years ago. We didn't evolve much intelligence since then. They were creative, smart humans.
That's possible.
well, it's still mysterious that, it's if you try to explain why there is one planet where we found intelligent life, it's still hard for science. Science would have an easier job with zero or many.
Harold, what planet is that has intelligent life?
Yeah, I know. When I've taught astronomy, I say there are many people who say there isn't even one. But
well, one of the saving graces out of this whole thing is just like the invention of the submarine way back when or whatever. Artists aren't constrained by the engineering principles and scientific method. And if you look at Star Wars and Star Trek and all those fun things, they say you're going to get there. You're going to figure out how to either go through wormholes. I never give you the explanation, but you got to get there. So you take that leap.
Yeah.
And just because we haven't figured it out, and I appreciate that this is an engineering community and you got a scientific method matters and yada, 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 but artists aren't constrained by that. And they've been predicting and saying that this is happening. And there's plenty of space.
Captain Kirk. Okay, I mean, Dave and I saw the whole series when it was originally on. Said, "Beam me up, Scotty. There's no sign of life here," and that has become a perpetual joke about why haven't they come to Earth? Maybe they have, and did not see any signs of life. And realize intelligent,
possible,
intelligent life,
or they saw us as we are, and decided we don't want to have anything to do with that.
That's right.
But I would like to throw a question out. When someone said, we've been smart for 50,000 years, what were we doing for 250,000 years before that? We were in the caves. We were here. Does anybody got an explanation for that? It's just that long to wire the brain.
With no scientific backing for it. You guys did a speech or one of your presentations maybe a couple months ago about early humans or early life, human type life.
Oh, good. Yeah.
Yeah, Denisovans and Neanderthals. Maybe that's original life. And what if we were visited? And then, as soon as you lose all the infrastructure support that requires to even be able to do this or way beyond this, it wouldn't take many years, hundreds of years, thousands of years, and you'd be right back in the cave. Only you would come with an oversized brain.
Mm-hmm.
And then you'd have to start learning again. So maybe the missing link is there isn't one. And there was crossbreeding. Just throwing it out there.
Oh, there was crossbreeding. Believe me.
Yeah,
My feet, my 6E feet are Neanderthal. I'm certain of
there
that.
you go.
It's,
Well, I think we're gonna close for the night, and
Yeah.
next week is John Wiltsey, and he hadn't as of last week decided on what he was going to talk about, but I'll get a hold of him and find out.
Mystery talk.
Good.
Yep. I hope you enjoyed this one tonight, and
That was good.
if we get more volunteers to do this, we could do this another time with the three talks.
I love it, Bruce. This is great. I hope you will do it again. You got a
Very
guy to
good.
talk 2 minutes,
Thank you.
10 minutes. That's got to be easy.
Yep.
If he has to talk 10 minutes, he's got to do that.
Okay. Thank you.
Okay.
Thank you, speakers.
Thank
Awesome
you.
job. It was really fun to hear you talk.
Yes, it was.
Thanks, everyone. Great
thank
education.
you.
Bye.
Hey,
Ripu,
bye-bye.
that was great.